So why is this such an infamous problem in quantum mechanics? Well, there are several different things that we can model with this particular problem. They're not perfect, but they're first order models for particular things. So let's think about what we talked about in physical chemistry last semester when we talked about translations. So we know that translational energies are basically continuous. The difference between energy gaps is so small that we can't even measure the difference between different energy levels, and we can get from one energy level to the next with such a small amount of energy that we can consider this as being continuous and that particles can have any energy. So this actually, we use the particle in a box as our model for those translational energies. So let's see why that works. So this is all predicated on differences in energy. So let's calculate the difference in energy between n plus 1 going to the n level, right? So let's go from E n plus 1 minus E n. That will give us a difference in energy between the n plus 1 level and the n level. And let's see how big that gap is. So n plus 1 gives me n squared plus 2n plus 1. That's n plus 1 squared, h squared over 8ml squared, minus the energy for the nth level. The nth level is n squared, h squared over 8ml squared. And that's going to be my difference in energy between any two adjacent energy levels. So if I look at this, I have n squared. I can distribute the h squared 8ml squared over this quadratic. So I have n squared times that amount. That's just the same as this term, so I'm subtracting that. And so my change in energy, my delta energy, my energy gap between any two adjacent levels is 2n plus 1 h squared over 8ml squared. So it takes this amount of energy to get from the nth level to the n plus 1 level. So first of all, let's look at what happens when m or L gets big. So when m or L, the mass or the size of my container, gets really big, then the denominator gets big, and that means that delta E gets really small. So for classical systems, so large containers and massive particles, then I never have to worry about the quantization, because my difference in energy levels is really small, and so I can consider this as a continuous distribution of energy levels. So that's why we can use this for translational motion, because we're looking at translational motion within large containers. So our delta E is going to be small because L is large. Okay, so we can use this for translational motion, right? Notice though that as n gets larger, the gaps get bigger. So as I go higher and higher in energy, this becomes a worse and worse approximation if m and L aren't really, really big, right? So I can use it for translational motion. That works pretty well. There's another thing that I can use this for, that I can model this for, and that's for conjugated systems. So the molecule beta-carotene, which I have pictured here, is the molecule that gives carrots its orange color. It absorbs in the green region of the spectrum, and the complement of green is orange, and that's why we see orange when we have this particular compound in vegetables or in other systems, but it's known to be in carrots particularly. So if you think about it, this is a conjugated system. And if you think about our picture of valence bond picture, all of these unused pi orbitals from these conjugated sp2 hybridized carbons, all of these p orbitals, right, are going to overlap, and the electrons, there are 22 electrons in this conjugated pi system. All 22 electrons are free to move about along this particular conjugated axis. So essentially, we have 22 electrons in a approximately 1.8 nanometer box. So we can model this by the particle in a box problem. And so we have n equals 1, we have n equals 2 level, we have all these different energy levels, right? N equals 3, n equals 4, they get further and further spaced as we go up, and then we go all the way up to, let's say, n equals 11, and n equals 12. So the electrons can't get out of the molecule, they can only go along this distance. And so our box is 1.8 nanometers long. That's how big L is. And each of these energy levels has an energy that's equal to n squared h squared over 8m L squared. And the particle that is in this box, the particle that is able to go back and forth here, is the electron. So we're interested in the mass of the particle, and that is an electron, so that's the electron mass. So we have 22 electrons, and 2 electrons can fill each energy level. So we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. So we fill up to the n equals 11 level in this particle in a box model. That means that our first transition, since all of these levels here are filled, I can't move electrons in to these levels. My first transition that I can observe is between n equals 11 and n equals 12. And so my delta E for that transition is equal to 2n plus 1 h squared over 8m L squared, where the n here is equal to 11 because I'm starting on the 11th level and going up to the 12th level. So that's the n to n plus 1 transition. So I actually have all of the numbers that I need to calculate that energy gap. So if I calculate that energy gap, just plug in 11 for n, plug in the value of h, plug in the value of the mass of the electron, plug in the value of the length of our box, 1.8 nanometers, I will end up with delta E equal to 4.3 times 10 to the minus 19 joules. Now, the photon that is required to make that transition happen, so the energy of the photon has to match the energy of the gap. And so the energy of that photon is hc over lambda. So if I want to know the wavelength of the photon that has that amount of energy, the right amount of energy to make that transition, I can solve for the wavelength of the photon needed to make that transition, and it's hc divided by delta E. And when I do that, I get an energy of 465, or a wavelength of 465 nanometers, which is right where I expect that peak of that visible spectrum to be for the beta carotene. So this particular particle in a box model works pretty well for big conjugated systems to predict where we expect to see what wavelength of light would excite that molecule and where we would expect to see the peak in the visible spectrum.